That was weird. I can get through this in about 40 minutes and definitely be done within an hour. So if you have any questions, you want to stop the process, you can go ahead and do that. Right, so the next slide. There we go. Okay, so here's the general outline about what we're going to present. There's a very brief introduction to the company because we're a relatively new company, even though we've been around in business for some time. And then focus principally on the technologies which are, I think, very unique to us. They're new. You probably haven't heard of them in the past half the webinar about methane inhibitors, why they're important, and how we've integrated them into our various technologies. And then the two technologies on the bottom, AquaBlok, Provect-OX, ISCO. Be a change of pace for that. Then at the end, just a summary of the presentation and a wrap-up. I think I've sent a PDF of this to everybody, but if we haven't, you can have a PDF of the entire presentation, so you don't have to worry too much about taking notes. And if there's anything you want to spend more time on, you're free to do that. Okay, so like I said, there's not a whole lot to say about Provectus necessarily in terms of history. So I gave you a little bit of overview on myself here. But I think the last two bullets are really the more relevant ones in that when I was with Dames and Moore, URS, we were working with W.R. Grace quite a bit on developing remediation technologies, pretty much for Grace-type sites. But that company went bankrupt, as you may or may not know, in about 2002. And then they spun off their internal biotech group to mutual fund investors. And through that, we took over the W.R. Grace Biotech Group and created Adventus Americas. So I was with Adventus for about 10, 12 years, developing the EHC technologies and the ISCR technologies and all of those, which have been widely used. We heard of. That company got sold to SM 2002, I believe, 2012, and in the last couple months or so, they sold that off as Peroxychem to JP Morgan Bank, which vision is not conducive to my vision, so I left that, and we created Provectus Environmental Products. And what Provect has are these patents that we've acquired from other people and other companies. Were issued, promulgated patents on various ISCR-type reagents, some ISCO technologies, and the methane inhibitors. And then since we acquired technologies, you could see in the orange patents that we've been developing, we've been expanding the reach of the methane inhibitors to the environmental industry and getting those introduced into our business world here. So that's pretty much the history of Provectus. We've been around for about 6 months, but we've been in this business for 20+ years. We're very familiar with technology.
Hey, Jim? Interject and ask everyone to put their microphone on mute. I'm getting a lot of back chatter, so I'm having trouble hearing you on some of the points here.
Okay, good point. Thank you.
Thank you.
I'm supposed to be able to do that on the phone, but I fear if I try that.
We'll just ask for the other offices. The other offices, I'm hearing somebody shuffling papers or whatever, and unfortunately it's coming in over you.
Okay.
Thanks.
Thanks for making that note. Okay, so even though we're small, we've been doing this for a long time. We have, mainly our offices are here in Chicago. We have an affiliate lab up in Madison, and all the other dots you see on these maps, besides South America, where we do have people, are through affiliates and collaborators and people I've been working with for my career. Okay, so let's get into the technologies now. First one we're going to talk about is the Provect-CH4, which is the trade name for the methane inhibitor that we've developed. But before we could get into that, I think it's useful and important to understand what this is all about. So, what's a methanogen? Some of this is simple, some of it's not, but I think it's very intriguing. A methanogen is an organism that makes methane. And we know from work done by Carl Woese from University of Illinois way back when that methanogens are their entire own domain. They are very unique. They're of the domain archaea, which means from a genetic perspective, they are very specific, very unique, very different from the helicocoides. In fact, as different genetically as the helicocoides are as you are. That meaning, for example, certain antibiotics will work on certain organisms and won't touch other things. Antibiotics don't touch viruses. It's the same difference in terms of genetic makeup, and that anything that you can, not anything, but particular things you do specifically to methanogens are not going to impact other organisms. We also know that methanogens are the dominant organism in most aquifer environments. They're naturally occurring. They grow the fastest. They're the most numerous, and they're pretty much everywhere you look in anaerobic settings. And they're important. We want them. We need them to be, members of anaerobic communities, which live as communities, and to help the helicocoides and other organisms, do their thing. So we can't get rid of them all. We just need to control them, and we'll get into why we need to control them. One, it's an immediate efficiency issue. If you go back and look at sites where you've done ERD, enhanced reductive dechlorination, with any amendment, lactose, whey, hydrogen-releasing compounds, EHC, lecithins, oils, you'll find that you made some methane. You made either small amounts or very large amounts of methane. And using this example here, just 20 parts per million methane, which is that bottom row. I think I could use this, yep. So if we make just 20 ppm methane in groundwater, which you're probably going to find if you look, that represents in this example that 33% of the amendment you applied got wasted. It didn't go towards the helicocoides organisms you were hoping to benefit from that. It got blown off as methane. So I think this is probably the most important point of controlling methanogens, is that it's a direct cost and efficiency issue. If you can control and minimize the amount of amendment you need to add to facilitate your remedial action. So, if there was one point that I think is the most important, it's this one, because it's the most common. When you do have health and safety issues, though, even though they may not be common, they become very, very important. One, methane's a greenhouse gas. Not everybody is, all too worried about that, but, from a sustainability perspective, some of your clients are very concerned about that, and they make note of it. Two, when we generate methane greater than 5% of the LEL, it can be problematic under buildings, slabs, and it can be explosive, and there could be major issues associated with excess methane production. And the next slide will show you a couple examples of where that's been observed. And we also know that with very active methanogens, when you're looking at heavy metal sites, they'll methylate those metals. And when we get to the Provect-IRM technology, I'll show you examples of where methanogens methylating heavy metals have been, I think, the problem associated with in situ precipitation of metal-impacted sites. The last bullet relates more to wastewater treatment. So here are, 1, 2, 3, 4, 5 examples of. I looked back into my project files, things that I've worked on in the past, and surveyed other consultants and other colleagues as to where they've seen problems associated with methane generation. And here are 5, very important examples. You don't want any of these on your desk as the project manager or the engineer of record. One, we had 2 subsurface fires start up immediately following the injection of a conventional ISCR reagent. And I'll let you figure out which one that was. And it was real. We did the calculations. We tried to figure out how that could be. Fortunately, it stopped after 2 fire events. No one could tell you what the source of the ignition was, but it was an old industrial facility, and obviously there was a buried line somewhere that was sparking and setting off the fires. So we had that very big problem. We're currently working on a site in North Carolina where they used Deramend, which is a ISCR reagent for an excavation backfill, and generating explosive methane concentrations immediately next to a church in North Carolina. So the state regulators are now operating an air-sparge SVE system, and they've been doing that for about 8 or 9 months. Monitor that quarterly.
Fire remediation.
They're pretty concerned about that one. For Indiana in particular, and there are other states that have their regulations either forthcoming or already promulgated, they state that if you exceed 28 ppm methane in your
get drunk.
Should mute their phone.
I like that one.
When they exceed 28 ppm methane in groundwater, you have to turn on your air-sparge SVE, which is a direct cost. So as the consultant, you're going to have the contingency in place, spec'd out and designed, and then be ready to go turn it on and install it and turn it on in the event that you exceed a certain methane number, which is going to be a real cost, and clients are probably not going to want to see that. Also seen changes in aquifer flow dynamics, and that I think is due to the gas bubbles themselves. We have excess bubbles and micro bubbles, and they'll change the hydraulics in your flow regimes. And that leads to excessive biomass accumulation, and that gets to be very problematic when you try to surge out wells, clean up your aquifer, and defoul basically the aquifer environment. The last example we have here is a large, high-rise real estate brownfield development that has been delayed occupancy for, I think, 6 months because oils that they added into the source area during the construction have liberated way too much methane, and they've had explosive concentrations under their buildings. So we're not the alarmist type saying you're going to have these problems in every project that you go inject amendment to the aquifer, but the point is that when it becomes a problem, it's a very real one, and they're very significant, and they can be very costly to you and your clients. And we talked about regulations. Indiana has them on the books. Other states have them pending. If you start poking around, because this piques your interest, you'll find them. Find that people are going to be starting to look at this and monitor it. So it's going to be something you observe in your course of business going forward. Okay, so that is basically the foundation for why were we interested in the ability to control methanogens during ERD or ISCR processes. So what these patents basically came up with or described was taking advantage of the knowledge that there are certain compounds known that will specifically impact methanogens. Red yeast rice extract is one of those. It is, if you look at that bottom yellow, this middle picture here, that's what it's describing. It's a yeast called Monascus purpureus. When you grow it on rice and ferment it in a certain way, it makes this red biomass or yeast mass. When you would extract that, you find that it contains a number of natural statins. The most important one that we've been working with now is called monocolin K. That you may not know as monocolin K, but you may have heard of it as levastatin and Lipitor, or things that humans have been taking directly for about 20 years to control their cholesterol. It's interesting that this statin interferes with the biosynthesis of cholesterol in humans. That becomes important when we look into the mode of action of how it's working on methanogens. It's also been consumed as red yeast rice pills. People take that as a natural amendment to help control cholesterol. And then we'll get to the cow picture in a minute, but we've been feeding it to cows for about 15, 20 years. And I'll tell you why we've been doing that. So red yeast rice extract is a natural material that we put into the amendment we call Provect-CH4 and others. known to inhibit the biosynthesis of pseudomurine, which is a specific cell wall component of methanogens. So bacteria make cell walls out of peptidoglycan or murine. Just think of it as their skin. And the methanogens make their cell walls or skin out of something different. It's called pseudomurine, and it is structurally almost identical to cholesterol. So when the statins interfere with the cholesterol synthesis or the pseudomurine synthesis, the methanogens in particular cannot grow or divide. So that is, the basis for the specific mode of action of the statins against methanogens. And this is just another picture of the same concept, where if you look at the green protein model there, if that's not being able to be made, the methanogens can't grow. So from a long-term development perspective, when I started studying this and thinking of it, I think the yeast have developed the ability to make these statins to control methanogens in their natural environment. It's kind of like germ warfare out there, bacteria trying to control each other and dominate the micro niche that they're in. And it just so happens that these statins impact cholesterol synthesis in humans. I can't imagine why yeast would develop that ability to help us. I think it's just the other way around. We figured out that these proteins inhibit cholesterol synthesis in humans, but the yeasts are making them and putting them out in the environment to control methanogens. Because if you remember, they're the most numerous and they're most dominant, and they're competing for food sources that the yeast also want in a natural environment. We also know that it impacts this F420 enzyme, which is, if you look down here, is very specific to methanogens. So in the process of making the acetyl-CoA and the acetate pathway, acetogens or dehalococoides use the NADH coenzyme, whereas methanogens are going to specifically utilize that. And some of these statins that are produced specifically target this coenzyme. So there's really two modes of action that the statins specifically go against methanogens. So that's the biochemical basis of it. So now we get into proof of concept of how it works for environmental applications. And here we're showing two bioreactors that were feeding on carbon sources for a couple weeks, generating large amounts of methane in the gas because we were trying to stimulate the methane production. In this one reactor, we added the Provect-CH4 methane inhibitors at 40 ppm. We did not add it to this reactor. So you can see after about 10 days, the amount of methane being produced in the reactor that was treated with the methane inhibitor went down to about zero. Nothing happened in the control. And then we added at 20 ppm the same thing in the second reactor, and you can see the slope's pretty much the same. So you can very quickly, knock down the methane production even in a very active methanogenic system. These data show at the same time the presence of the methane inhibitors did not impede or impact the growth of dehalococoides after 25 days. There's the control, and this was inoculated with the CB&I culture, SDC9, but it's going to be the same as pretty much any other dehalococoides culture. And it makes sense. If you remember the mode of action, it's going to be specific to methanogens in their cell walls. Dehalococoides make their cell walls completely differently. So it shouldn't impact them, and it doesn't. These are data we just got back from the Naval Research Lab showing that aerobic facultative anaerobes and things like pseudomonads, which are also important for biodegradation and bioremediation, are not impacted by the presence of statins either. This is at 10, 25, 50, and 125 ppm. And I show this because when we look at field applications, we target about 50 ppm of Provect-CH4 in groundwater. If we have a very active methanogenic community, because you're going out there trying to fix a problem that we've created using another amendment, for example, then we'll put in 125 ppm, a higher dose, because that does seem to do a little bit more in terms of not just controlling, but also inhibiting methanogens. So that's kind of the basis of the two numbers we'll see in application rates. It's 50 or 125 ppm. And these data were tritiate and leucine uptake, so they're very direct indicators of how fast an organism is assimilating biomass. So then a fair question comes back as to, okay, if you're knocking out methanogens, what's the fate of the hydrogen and the volatile fatty acids and everything else that we're doing? Where are these gases going to go? And this is where you go back to the cow you saw on one of the earlier slides. If you look at the dairy industry, they've been feeding red yeast rice extracts to cattle for about 20 years now to control rumen microbiology. Here they weren't so worried gases coming out the back, but they were trying to prevent methane coming out the front because it impedes the cow's ability to be efficient in feed assimilation, and when they burp, these acidic materials and all that rots their teeth. So they can't fatten up fast enough, and they waste food. So if you look at what we know about rumen microbiology, this is what's going to happen. You're going to knock out the methanogens, which they do effectively, and then the acetogens survive, so do sulfate reducers, nitrate reducers, and our dihalococoides organisms and other dehalogenators are going to have a much more easier that we're trying to generate for them. So, it all tends to flow somewhat reasonably if you consider all of that and see the potential value of not eliminating all methanogens, which we're not proposing. I don't think we can do that, but effectively controlling them. So that's what Provect-CH4 amendment is meant to do. It is red yeast rice extract processed in a special way for the environmental industry. It ships out in these 50-pound or 25-kilo buckets. It's a dry powder. It's cold water soluble, very safe and easy to handle. People have been eating it directly for 20 years. We've been feeding it to cows for 20 years. You add it to your aquifer system, and that will go out into the environment and control the methanes, the methanogens, and the methane production. That's just a picture of the material. This was with an EOS application where they've had problems with too much methane being produced out on this site. So pretty simple, pretty straightforward. We got one case study that I can share with you to date. This was a dry cleaner site, former dry cleaner site in Georgia. This was the former dry cleaner. Groundwater is flowing this way. We did two things here. At this well, which is here on top of the hill, cross gradient to the PCE plume, we added ABC, which is anaerobic biochem mix, redox tech cells. That it's just an ERD supplement that has been widely used for a long period of time, very effective. And we added the methane inhibitor at we targeted 50 ppm into this application. Here at this well, NW4, they added just the ABC ERD amendment in about 15 feet up gradient from that injection well. This was also added about 15 feet up gradient to that injection well. So we added the same amount of amendment, just at this well we added 50 ppm of the methane inhibitor. And these data show the results after 6 weeks of a treatment. Up top we have the dissolved gases in groundwater, where we added the methane inhibitor, we now have 4 ppm, went from about 12 to 4. Where they did not have the methane inhibitor, went from about 14 to 10. The lab lost the PCE samples, so I don't have those data, but we are generating more. We also took these two instruments and just went out and smelled the gases from the wellheads. And these are the data down here from those measurements. The TVA FID PID analyzer blew out from the very high concentrations of methane. So that one, even though I think it's more sensitive at the lower concentrations, if you're going to these sites where you're expecting methane to be produced, you're better off using this landfill gas meter. And that meter showed us that we went from about 35% methane in the wellhead gas to 0.5% methane in the wellhead gas. So very notable, very real differences. And this this 35 ppm or 35% methane was right here immediately into the entrance of the strip mall. So, it goes back to one of those, it could be a big problem if, luck just goes south and things go bad. We really can't be having that much methane generated in these types of situations. And I think the more you start looking at your sites, the more you're going to see those types of situations. And I just think as an industry, we should be more, we should just be watching that, I think, more closely. And in the process of watching it, this is where companies like CRA and the other consultants really have to help out, because I don't think there's one site that I've done in the last 20 years, ERD or ISCR, where we've had sufficient monitoring systems to look at this. Because monitoring methane and soil gas is completely different from what we've been monitoring historically during our remedial actions, which are groundwater systems. And that's kind of just shown at the cartoon here, where, if this was the area you're trying to control methane, and we added the methane inhibitors, and we did a job, we effectively controlled it, you're not necessarily going to see that if we're pulling, for example, soil gases under slab with the SUMA canister, because you could be pulling those gases from, over here, where you still have very active methane generations. And so when we start looking at this more closely, and the consultants start putting this into some of their plans, we're going to have to do a better job at setting up the monitoring network so that the data we get represents the situation and that could be interpreted fairly. Because that's a real challenge, frankly, right now. Even the sites that we're going to, in the last month, you look at the monitoring network that we're trying to pull the data from, and it's really not ideal. We're going to have to rely most heavily on just dissolved gases and groundwater samples. Okay, so what does it cost? That's always, a fair question, and it's an important one. This example is meant to show where we're adding the methane inhibitor alone, Provect-CH4, to, for example, a lecithin site or an oil site or a site where we just added carbon for a period of time when we have a methane problem and we're trying to control it. So they needed, an example, 90,000 pounds of remedial amendment, either E1, and I just use a price of $1.50, and I think that's a fair average price. So that would have been $135,000 just for the amendment to treat this site. We're going to take advantage of the fact that we mentioned early on, at least 30% less amendment is going to be required just from the efficiency issue. Again, that should be maybe in red, because I think that's the most important point. And I think that's a minimum number. It's at least 30%. But just taking 30% less amendment means we save $33,000. We don't need 90,000 pounds. We could get by with 67.5. There is a cost of the methane inhibitor alone, and for these applications, it's $35 a pound, which means you've added $24,000 to the ERD only costs, which represents a premium of, say, 15% if you didn't do it. But for that premium, you've avoided or you've minimized this need for the contingency planning. And if you ever had to turn that system on, it clearly saved money. To turn on that kind of air sparge SVE and run it for a year, or delay your building occupancy, or to have a fire start up, is going to cost you a whole lot more than $20,000 from the methane inhibitor. There's going to be a similar table in a minute, which talks about using the amendment that we have that already includes the methane inhibitor, and these numbers are going to be even more favorable. I think that's coming up right now. Yep. So that's what we were looking at. We really don't want to have the main technology be reactive, in the sense we're going to a site where we already have this problem and we're trying to control it. I think there's a market for that, but that's really not where we want to be. I think we're better serving ourselves if we could just be reactive, proactive in the sense, and control it to begin with. So for a liquid anti-methanogenic ERD amendment, we had the choice as Provectus as creating our own. but I made the decision, frankly, that there's too many out there already. I mean, there's so many flavors of carbon sources you can add. The industry didn't need another one. So we looked for, people who understood it, saw the value in it, and were willing to collaborate with us. And Redex Tech basically saw that right away. And so their anaerobic biochem mix, we added the methane inhibitor to that and came up with ABCCH4. And that kind of is what I just said on this slide here. So we really don't want to be out there responding to the situations in some of those slides. We'd rather be doing something and add an amendment more proactively and better designed. So that's what ABCCH4 is. It includes Provect-CH4 into the amendment that you buy, which is a liquid ERD supplement. It could go right downstream wells, and there's enough of that methane inhibitor in there to target 50 ppm of the red yeast rice extract in the groundwater. Yeah, you can look at these when you have time. It just talks about liquid ERD amendment, some of the benefits of that, but I don't think there's anything new there that you guys want to know. And I think it's more important now to look at then the economics of doing it this way. We're not charging $35 a pound anymore for that. It's now $1.80 a pound for the methane, the ABCCH4. That includes the methane inhibitor with it. So again, we're taking advantage of the efficiency issue. Say we only need 67,500 pounds of this amendment, even though it's a little more costly. If you write the numbers out, it shows that you're directly saving $13,000 compared to doing just the conventional ERD amendments alone, regardless of what you're using, and this being the standard price. So this is where I think it becomes more attractive from just a better design perspective, better serving our clients' perspective, and also from a cost perspective. Okay, so that was the methane inhibitor, the liquid ERD amendment, and now we'll spend about 10 minutes on the revised ISCR reagent, which is the solid antimethanogenic material just for carbon, just for organic contaminants, and then metals and organic contaminants. Okay, so like I said early on, I developed this BHC stuff about 10, 12 years ago, and it hasn't changed since I left, which is about 6 months ago. It's pretty much the same formula, the same thing, and it's very good. It worked very well. If you used it, I'm sure you know that it's different in terms of applications, but it's a very effective technology, and it works well. But by controlling the methanogens in the system, it makes it an even better technology. And that's what Provectus is all about, trying to take these things to the next generation, but having it be generally different, not just a new flavor of something, but really being different and having a benefit to using something like that. So this is what the ISCR amendments do. They actually have zero-valent iron as part of the amendment. So it's not just another reductant, but it's a true zero-valent iron particle. And there's real benefits to having that in the formation. When you combine that with carbon and iron, you get many different reactions that take place. You get very low redox conditions. Things are very active in terms of treatment, but we still have this problem with methanogens. They're there. This talks a little bit about the ISCR process. We've been talking about this for a number of years, and I don't think there's anything new here. It's the same thing. You've got the carbon and you have the iron reactions. You get all the benefits of the synergistic ISCR dynamics, and the treatment process is the same. All we're trying to do in this generation of the ISCR technology is deal with the methanogens that are out there. And it kind of makes sense when we put the ISCR reagent in that we've seen these significant methanogen blooms, because if you look at the conditions we create, near neutral pH, EH down to minus 275, minus 350, depending on how you measure it, that is the perfect spot for methanogens to grow and bloom. And if you look at the table up top, it shows that methanogens are going to double, they'll double their number in an hour, whereas the organisms we're really trying to grow, the Helicocoides type species, take 24 to 48 hours to double their numbers. And so, that's a logarithmic thing that you can imagine, and, surely within, a number of days or a week, the methanogens have totally dominated that whole aquifer setting, those micro niches, and it's very hard for the Helicocoides to compete with that, which I think has been part of the problem we've seen when we get, the DCE stalls or the inefficient treatment. The response is, well, you need more amendment. I think that's the wrong response, because all you're doing now is, continually feeding the methanogens. So, that there is a real benefit to keeping a lid on these, controlling them in the process. And so that's what the Provect-IR solid antimethanogenic ISCR reagent is all about. It still has the carbon, still has the iron. There's a couple more improvements we made to it, but primarily it's got the methane inhibitor added to it so that we can knock those guys down. And then you get the same benefits we talked about in terms of efficiency, which I think, again, is the most important benefit of the technology. Where it is a problem in terms of safety, they're significant, so you get to avoid that. And you get to avoid, the potential regulatory issues, heavy metal methylation, which is a real issue, and then you get secondary COI issues associated with, methanogens being out of control. So that's what Provect-IR is. It's very similar to EHC, which I developed 10 years ago, and if you saw it, you really wouldn't see any difference. That's our Provect-IR. Some of the improvements we've made, we have different plant materials in there as organic substrates. One of the patents that you saw on the table earlier describes kelp and seaweed and algae as a source of carbon. And there's a real benefit to that, because marine plants, have a different profile of them than land-based plants have. So, B complexes, there's other vitamins and minerals in that anaerobes really like and need. And so there's a component of that to it. Different release characteristics, different composition profile. We also have very small iron particles. We're not into the nanoscale world because there's reasons to not do that. But, we don't want 100 micron iron or 75 micron iron, because that gets really chunky and causes problems with mixing and settling and injections. So if you look at that material, it's very fine, very easy to use, easier to use than some of the other materials that are out there. We also integrated a chemical oxygen scavenger into this material, because when you're mixing the solutions in water tanks above ground, you're aerating them. So it makes a lot of sense just to have that whole slurry be reduced when it's injected. So you don't have to consume material or wait for the aquifer to go anaerobic because you introduced a lot of nitrogen or a lot of oxygen just during the construction process. And of course, it's got the red yeast rice, which is probably the biggest differentiator between them all. I put this in just to remind people that when you're adding a solid amendment like Provect-IR, it's different than adding a liquid amendment. We're actually putting it in via physical displacement. You've got a slurry of a suspended solid that goes into an aquifer formation. It stays in place. It stays reacted for a long period of time, 3, 5, 7 years. And it's not looking at pore volume displacement. But that's a different talk altogether. And this table summarizes Provect-IR against conventional ISCR reagents. This originally said EHC on top, but I got a letter from their lawyer saying they didn't like that. So, but it's EHC, and these are things that you can look at and just compare side by side And I've highlighted things that I think are very notable and that the other group seemed to not understand when we were putting these original tables out. So those are the highlighted differences. And they're very real. It's just fact. These are very real, very significant, I think very important and useful differences. Okay, so if you look at Paul Tratniak's table, where would you put Provect-IR? I think it falls in there. This is a very good article. I've got a copy of it if you wanted to review it. I'll go through that.
sRGB.
Pardon me? Is that a question or just... Okay, no question. Provect-IRM. You look at heavy metals now. We know that these metals that are listed will precipitate out onto iron particles as iron sulfide precipitates. It's been effective, very effective on chromium, things like that, but it's been partially effective on arsenic. And that was of particular interest to me because I had a couple arsenic sites that I was working on, and they were very confusing in that things would go down. They would never go down to the levels that we anticipated or, quote, they should, and then you'd get rebound issues and things like that associated with it. When Provectus came along, I started looking at that much more closely, and I went back through some of the data sets and asked some of the consultants to generate more data, and sure enough, this is what we found. The residual arsenic, or the arsenic that was being found, a year or two after the initial ISCR treatment, was methylated. It was all organic arsenic species. If you go back to the literature, this one goes back to 1945. I didn't know it. I found it a couple months ago, but you see that methanogens are known to methylate these metals. They'll methylate all the metals, including lead, but it's hard to find lead examples. So when we did the residual analysis and we saw all the methylated arsenic was what was the soluble arsenic, it became pretty clear that we were causing part of the problem. It wasn't that the arsenic couldn't precipitate or wouldn't precipitate on the iron surfaces, is that we've methylated it, and that is not going to participate in the immobilization reactions. So that's what IRM is all about. It's still exactly the same as the other materials. In this case, it was EHCM that they added, but if you inhibit or control the methanogens, especially early on in the process, we'll avoid generation of the metals and much better immobilization process for not just arsenic, but for all the heavy metals that we're trying to treat. Okay, so let's say I got 5 more minutes. I'll wrap this up. AquaBlok, you may or may not know about that. That was an application that we pulled together with the AquaBlok company. And so what they have is a rock that they surround with bentonite. You put that rock through a water column, the bentonite swells pretty quickly, and you get a very competent, very impermeable cap within a matter of hours. So those are the rocks. That is what it looks like a couple hours after hydration. That's about the 10 to the minus 8, 10 to the minus 9 centimeter per second layer. And this is about a 3-to-1 ratio. So if that was 2 inches, this would have swelled up to about 6 inches. You can drop them through water columns. They sink like rocks because they're rocks, and they form a uniform barrier along the sediment, hydrate, and you've got a cap. And that's just an example of a coal tar AquaBlok cap above it. After 3 years, they sampled, and sure enough, the coal tar's still there, and nothing came up through the top. Clean sediment redeposited on top. Going back to these applications, though, and working with the AquaBlok guys, we've known that immediately upon addition of this, and it's not just AquaBlok, it's with sand caps or membrane barriers or pretty much any cap you put down, you stimulate the methanogen just as part of the application. You're just mixing them up, adding things, and you get a lot of methane production. You get ebullition. That gas is going to go somewhere. It can either blow through your cap or it travels downstream somewhere and gives you sheens where they weren't before. and it was very problematic in situ sediment capping. They had a number of engineering designs. There's a couple companies that have patents on, how you can control the gas migration during the whole process. But our idea was, again, let's just control that early on in the process by putting some of the methane inhibitor into the AquaBlok material. So as it goes down over the sediment, and it doesn't have to be long term, just at least short term, controlling the methanogens, not allowing them to become, overproductive, overactive, and generating too much methane. So that's what the AquaBlok CH4 Antimethanogenic capping material is all about. So if you work on sediment caps and in situ sediment treatment, I think you'll see some potential value to that, and it might be something you want to consider. And I'll go back. So these reactive gates, the concept there is you got an impermeable horizontal barrier. You force the water to go through a certain treatment gate, and that's very similar to what we've been doing with groundwater systems for 20 years, where we have these types of reactive PRBs. Now you got a horizontal reactive PRB, and it just rides on the same technology and the same principles for what we've been doing for a long period of time. Okay, the last thing I want to tell you about is our self-activating ISCO reagent. So this is, completely different from what we've talked about today. This is now an oxidant. And I'll tell you why I think it's something to think about and why it may be something to consider in your ISCO projects. We're using sodium persulfate, but we're activating it with ferric oxide, and that's the nature of the patent. We firmly believe this is an independent patent, and it doesn't have any impact on the other existing patents, and so we are free to buy our persulfate from whomever we want to buy our persulfate from, which means you get it at a better cost. Its mode of action is unique in that we've got sulfate radicals and ferrate radicals being generated, but the nature of the patent really rides on the fact that the iron cycling reactions are going to enhance the natural attenuation process once the initial ISCO reactions are done, because the persulfate radicals and these radicals, generally speaking, it's a matter of a week or two before that whole ISCO process is over. But for hydrocarbon sites, we've seen significant rebounds come from that because you don't have anything going on thereafter. You have some sulfate reduction, but that's probably not the best way to treat residual hydrocarbons in particular. So by using, the iron, we get those transitions back and forth from ferric to ferrous, and we can then have longer-term sustained secondary treatment of enhanced bioremediation post-ISCO. So I know the use of oxygen-releasing compounds with persulfate generally rides that same theme, but the oxygen-releasing compounds themselves, they have pH of like 12, which I understand that. My background's in that, and I know it's not going to be pH 12 everywhere, but organisms don't like pH 12, and the oxygen that is liberated from that doesn't last nearly as long as the iron cycling reactions are going to last. The other notable point is that, once you've added this to a formation, if you have to go back and add more persulfate, you don't need to add more activator because the activator is already in there, because these iron particles aren't going to move very far, and they're going to stay present in the formation where you've added them. And it's safe. It's safer. We don't have extreme pH. We don't have caustics on site. It's much easier to handle. And I think it's a better oxidant for certain applications, and it might be something you want to consider for some of your ISCO. And then there's a case study here on the oxidants for the site. You can go through that on your own. There's really nothing new. It worked. It seemed to work pretty well. These data show the longer-term sustained effect of the secondary electron receptors present and their activity over time. Okay, to wrap it up, you guys have these slides. This is paper I wrote with Dick Brown way back when, and I put it in here and summarize some of the tables, mainly to note that things haven't really changed. The technologies we have still fall into this box. I think the ISCO-ISCR selection criteria are still the same. We haven't modified any of that. You could go through this on your own if you have an interest in time, and if you want, I can send you the paper, because it's a pretty good summary of what to consider when and where. Okay, so to wrap it up, we have the new ISCR technologies. We have the methane inhibitors. The same way we operated when I was at Aventis, we offer you complimentary site evaluations. Pretty much means you say, okay, here's my problem, here's my site. What do you think? And we'll give you, the conceptual or remedial design. But that's, going to be like a 15% design. It's not a design. It's just, here's where we think you can add your amendments, but what it will give you is a material selection and a cost for the amendment that we think you might want to use. A little bit different from what I did in the past is we're offering formally these complimentary data review on a quarterly basis for each job, mainly because the monitoring here it's more complex. A company like yours probably doesn't need the help, but there are others that, I think, we should give them the benefit of things we think we know and our experience, because when the data come back, we want them to be something that are useful and that we can interpret. And if you remember where those methane wells are at and how you monitor methane, if that's not done right, and things come back inconclusively, no one really benefits from that. So we'd like to try to avoid some of that. But like I said, you guys might not need that as much as others. Through the lab up in Madison, we can treatability studies, and through some strategic partners for injection contracting. We've done this with Orin, IET, I think with ARS, we talked to them a little bit. They're all willing, Redox Tech is one, they're all willing to team up with us and offer you these contracts. But as you know as well as I, it's the specifics of those contracts, and they're all site-specific as to what the value really is in terms of the guarantee and warranty and what happens when things don't go exactly as planned. Okay, so thank you very much for your time. Appreciate your hour, and it saves me a lot of time, and it's a much easier way to get the message out to people as opposed to flying around to each office. So if there are any questions, I could try to answer them. Hello?
Hi, yes, Jim?
Yeah.
Hi, yeah. This is Emily Jackson in the Baton Rouge office. And where was the presentation?
I will send it out, if it didn't go out